Today, I'm going to talk about our project called Limited Linking Kindergarten, which is very popular in around the world, and in Chinese, it's called Lian Lian Kan. First, let's look at these pictures. These are the game we play when we are young, and does it call your nostalgic childhood memory? This is our table of contents. Next, I'm going to talk about the introduction, the demo, and the teamwork. First, the introduction. In fact, Lian Lian Kan is a very traditional puzzle game. It requires the user to choose two grids with the same picture. For example, in the right picture, there are two grids with the same picture, and if the path that's linked to grids can turn direction in 0, 1, or 2 times, then we call these two grids are cancelable. And this game is very complex. The first question is, we don't know how to tell if the two grids can be cancelled. If two grids are close to each other, it's easy to say they are cancelable. But if they are far from each other, and it may take the path may turn direction in 2 times, this time it's very hard to tell whether it's cancelable, and we need to find a link algorithm to solve it. The second problem is about the timer. We use a timer to calculate the total time, and if the time is finished, the game must be finished. And we also want to add some more features to the game. For example, if you cancel two grids successfully, then we can add several seconds into the total time. Next, I'm going to make a demo. This is the main page of our game. You can see score here, and you can make some setting here, and you can choose the total grade to be 2, the total game size of the grade to be 2. Then we start this game and input the name Li. In this game, you can just click this and you finish it, and the total score is 60, and we can restart it again. You can see from the top of the game that we have a timer bar here, and we can use hint to give us some hints of the grids that can be cancelled. And then to score, you can see my record is recorded here. And this is the demo of our game. Let's move on. This is our teamwork. We distribute our jobs very. We distribute our jobs to the teammates, and we cooperate with each other very closely, and we communicate with each other very efficiently on the GitHub or on the WhatsApp group. Next, this is the whole class diagram of our game. You can see from the center that we have an abstract class, abstract page class, which all the GUI pages extends from it. And we have 5 packages here, and we have 5 packages here. Each package are divided into for some specific use. Next, I'm going to make my teammate to talk about the project plan.
The plan. First, I will talk about the software development methodology we applied. As we know, the task-driven method is one of the most common and practical methods in software development. So we choose this method without exception. With this method, the project can be divided into different tasks so that each member can implement the respective task simultaneously, which also facilitates the formulation of the project plan and the whole project management. Of course, during the implementation of the project, we kept adjusting our plan according to the specific situation, such as the task progress of each member. We first discussed what software we want to develop, and after deciding to launch a game, we have made a relatively careful research of the existing finished products of the game. Specifically, analyzed the function of the game and then started to design the frameworks including algorithm, logic, GUI, and UML diagram. After that, the most complex and important task is the game development. We first developed the terminal version to realize the algorithm, hammer, and logic, so as to prepare for the GUI implementation. In this task, we implemented homepage, game page, score list, and game setting respectively, and finally integrated them together. For the last phase of the project, we needed to test the game, fix bugs, do code refactoring, and documentation. We followed the prescribed order to perform unit testing, integration testing, and system testing, and ensured to maximize the coverage as soon as possible. After that, we documented all the work of this project and finally generated the project report. And this is the work progress chart of our whole project, which clearly shows the different stages of our work in 3 months, and the tasks and the progress of each member in each stage. In the future, we would like to implement several functions in order to enhance the application. Maybe we will add the background music to make the game more enjoyable, apply different modes to the game, and the user can choose to play different modes before starting the game, and animation after each canceling to make the page vivid. Use database to store scores to avoid tampering the scoreboard.
Hi, I'm David. Next, let me present the procedure of designing and developing the main game logic, which includes system design, program flow, code refactory, design principle and patterns, and unit test. First of all, the system design. Here is the procedure for us to design the main game logic. First of all, we did a research about the traditional LLK to find out the pros and cons of the traditional game logic. Most of the traditional game logic is checkpoint. If you pass the first game, there will be a harder game. The problem is it's boring to play first few checkpoints, and once players finish all the checkpoints, it is meaningless for them to continue playing this game. Therefore, in our design, we add a scoreboard and game size setting to make sure users can choose the difficulty themselves and record their score history. And according to the first two steps, we wrote a use case specification to further analyze the user requirements. After that, we designed the GUI logic, which includes the relationship between different pages, to make sure the game operation is user-friendly. Here is the use case diagram to show what the program should do. There are 17 use cases in total, with 3 actors: the user, computer timer, and the file system. The details can be found in our report and also the use case table. And here is the logic diagram to illustrate the relationship between each pages. The main page is what you will see after running the program.
And there are three buttons: Start, Scores, and Settings. Press Scores button and you will see a score dialog to show the history top 10 record of your history score. And press Setting button, you will see a setting dialog. And you can set the game size in the game size picker and also see the author's information. And press the Start button, you can start a new game. First, you will go into the pregame page. Here you can input the username and submit to start a new game. And the game size of the new game, it depends on the setting dialog. You set it. And also you can press cancel to return to the main page. And in the game page, there are three buttons: home, restart, and hint. Press home button, you can return to the main page, and press restart button, you can restart the game page. And you can also press hint button and uh, arbitrary pair of the cancelable grids will be shown. And you can also play the game. If you cancel all the grids successfully, you will go into the success page. And if you run out of all the timer, you will go into the fail page. And in the success page and the fail page, uh, there are also three buttons. Press home button, you go to the main page and press score button, you will see a score dialog, which includes a previous game record. And press the restart button, you will start a new game. According to the game logic design, we have a first implementation of GUI, i.e. the release 2 of limited linking kindergarten. Logic between pages are too complex to be completely presented, so I will choose the main page as an example. In release 2, the program flow of the game page logic is firstly call the constructor to create new J buttons. For example, here we create score button, setting, and start button first, and another function called adapter will add action listener to each one of the buttons. According to the previous logic design, there will be dialogues for settings and scores, and also a new page for the pregame page. So therefore, for dialogues, the dialogue will be presented by using the setVisible method, and the main page will not be disposed. And for the pregame page, first it will be shown visible, calling the function, and also the original page will be closed by using the dispose function. So then let me talk about the code refactoring according to the previous release. In the old version of main game, the G button label need to be set inside each page. Each game page will have a messy dependency association with each other. For example, the score button. The score button is used to link the score dialog. In the old version, we have to implement the action listener explicitly in the adapter method, which is so messy. Besides, if we want to initialize next page by using states of the current page, for example, in the main page, we want to initialize the pregame page in the banded to the start button. We need to first let the main page implement action listener, which is not a good design. Here you can see you have to implement the action performed and initialize the pregame page in the game page. In order to lower the coupling between pregame page and the main page, we extract the button as a class. make every page that banded button implement the interface called button bandable. Mm, then we can make the button bandable uh, and to decorrelate the pages. Then those buttons inside the main page do not need to call the function of other pages anymore. Besides, in the old version, we found that the game information will be passed uh, to the pregame page by using the constructor. Um, but as an individual module, pregame page should be separated from the main page. So there should be another method to get the information. And we cannot hard coding the parent page in the pregame page. So we use the abstract page. We extract the abstract class, which has an abstract method called getInfo. The method is used to get the information from parent page to the child page. So you don't know who is the parent, but you hold the reference of abstract page. So now in release 3, for show button method, we can simply create new buttons and create new pages and band them together and add the banded button to the main page, which is simpler and more intuitive. And the band method is implemented in the button, which is extract from the previous version of button. The band method will add action listener according to the banded button bandable object. So we need to implement the refresh and display, which is defined in the interface. For example, the pregame page. The refresh method, you can find that the refresh method run the getInfo method from the parent page and prepare for the corresponding game page according to the game size obtained from the main page. And for display method, the pregame page will get location of its parent and set the location to itself to make sure the two game pages are exactly in the same position in the window, and it will close the parent page. Finally, it will set itself to be visible. So as you can see, there are so many methods. Actually, these methods are uh, in the previous version, they are in the uh, adapter method. So we extract them to the pregame page, which decorrelate the pregame page and main page. So here is a code in main page after refactoring, which is more readable and reasonable than the previous one. You can simply create new buttons, new pages, and band them together and add to the main page. So then let me briefly show you the design principles and patterns. Uh, First of all, for some pages, singleton is used to save the results. For example, the game page. As you know, each game page will have a timer. So if we do not use singleton, there might be a lot of game pages, and each game pages have a timer. We have a lot of timers. And the timer is actually implemented by using the Java multi-threading. So we have so many threads, which is computational expensive. And secondly, each page class in the game will extend an abstract class called abstract page, as I mentioned before. So this class is a model of all subclasses. Design in the diagram meet the requirement of OCP. It opens for extension and closes for modification. If engineer would like to add more pages to the game, they only need to create a new class derived from the abstract place instead of hard coding. Also, this graph shows the DIP. Uh, we can find that here the button bendable interface, which hide the information from hide the information uh, between each pages. As the previous example shows, we directly construct the pregame page in the main page. So now we simply use button bendable as an interface, so we can perfectly separate the information. And the previous game page and the main page depends on the abstraction, so which is the definition of the DIP. And last but not least, abstract page class does not have any function that its subclass cannot implement. It meets the requirement of LSP, which is the fundamental base of OCP. It requires all the subclasses inherited from the same abstract class and implements all the abstract methods. So last, let me talk about the unit test. So as you know, all the page classes represent how user could interact with GUI. However, the question is we cannot monitor user click in the test cases. So some of function will only be called after the specific button is clicked. So it is really difficult for us to test GUI. But however, we spent a lot of time and finally get a coverage of 88.7% unit test coverage. So, and we also have a test set containing 8 test cases. I think we tried our best to test the GUI part. So that's all of my presentation. Thank you for listening.
Let me talk about the design of the game board for LLK. Like the main game, I'll base my talk on the following parts: the program flow and algorithms to solve the problem, design principles and patterns, code refactoring, and unit test for this module. The first major challenge for the game board workflow is to generate a solvable board with solvable grids. Here, we define the state of solvable as a board should have at least one pair of grids that can be cancelled. Otherwise, we say that the board is illegal and should be adjusted. The board is unsolvable. The second challenge is to design the interaction of cancelling grids with the users. Details of cancelling interaction will be introduced later. To generate solvable grids, we create a pool of images. We fix the position on the board for selection and select a random image and bind it to the grid. For example, if we want to have a 10 × 10 board, we'll pick 10 images, each of which occurs in the image pool for 10 times. Each time the board performs a random selection, the selected picture will be removed from the pool. In this way, all grids on the board will be of random type, and the number of each type will also be even. In our implementation, if the board is not solvable as defined before, we will shuffle it until it is solvable. For the cancelling interaction, we have two major challenges. The first one is to select the grids where the mouse is clicked on. It means when you click your mouse on the grids that you want to select, we have to tell you that this grid is selected. Also, we need to deselect the grids when player wants to change the selection, or he or she selects a pair that cannot be successfully cancelled. We should also tell if a pair of grids can be cancelled. The strategy for solving this problem is to add borders for selected grids and remove the borders for deselected grids. We'll also need to register the event to a mouse handler in Java and to execute the corresponding methods whenever the mouse is clicked on the grids, so that the selection, deselection, and cancellation will be called whenever the situation is suitable. This is the sequence diagram for the part of canceling selection. It is implemented in a mouse handler. We basically split it into two branches depending on if there exists a selected grid on the board. If the board is the second one to be selected, we'll further consider if they can be cancelled. All the algorithms are processed corresponding to different cases. Next, I'll talk about the design principles and patterns used in the design of the game board. We mainly try to conform to the dependency inversion principle, and we implemented command pattern for the game board. As the cancellation process on the board depends on the algorithms of judgment, if these algorithms change their implementation, the board also needs to be modified. Therefore, to reduce the coupling between the board and the algorithm, we split the algorithm out by creating an interface used by lower level class. The lower level class is the linking algorithms. In this way, the higher level class, the board, doesn't need to depend on the lower level class, the linking algorithm. Using the command pattern is also aiming at reducing the coupling among board and other classes. We set a grid as command receiver, and executor, and design 3 concrete command classes to select, deselect, and cancel the grids. Board registers commands with the command pattern. The board registers the commands with the command manager, and the command manager itself will call these concrete commands. We refactor the codes to follow the design principles and patterns talked just before. To comply with the dependency inversion principle, we extract the linking algorithm and the grid out of the board. In the former release, you can, as you can see in the picture, all the algorithms are directly implemented in the board class, and grids are just used as JLabels. And at the latest release, the grids are inheriting the JLabels, but added more methods and overrided some methods. We extract these components out to reduce coupling. As for the command pattern, I shall show you how to call commands from the board class, which is the client of this pattern. Before refactoring, we just directly call the functions on the grids, so that we just directly use the receiver to call the functions. But after the command pattern is added, we first register these commands with a newly created command manager like this, and use that command managers to execute all the commands. In this way, both spatial and temporal coupling among the classes like boards and linking algorithms and grids are enormously reduced. Finally, we'll go through how we perform unit testing on this module. I'll talk about how we test the linking algorithms, and my teammate will explain the remaining parts. The aim of testing linking algorithms is to make sure that that algorithm will return the correct linking path and tell correctly if the grids can be cancelled. We design a minimal set of that contains 6 test cases, and we successfully achieves branch coverage. The design of the test set contains different ways of cancellation, like 1 line, 2 line, and 3 lines.
Hello everyone, I'm Dong Qihua, and now let me talk about the situations in testing Guido Java. Here we achieve 100% unit test coverage by using 7 test cases. Guido Java is a functional object, so we can just use the most basic method to test it, constructing the object, calling different methods, and checking the results. But things get complex in Bottle Java. Bottle Java is a GUI-related component that is responsible for representing the ball. And here we achieve 96.7% test coverage, which is quite satisfactory for us, since it's really hard to test a GUI component. And we really put on a lot of effort. We write a large test set. For one hand, we need to create some GUI component stuff to call as many methods in Bottle Java as we can to test whether they can function normally and to increase the coverage. For another hand, the game situation is quite complex, so we need to iterate through as many game situations as possible to gain a high coverage and to walk through as many paths as we can.
Hello, my name is Harry, and I'm responsible for the development, testing, and documentation of Timer. So my agenda will be like follows. I will talk about the program flow and algorithms using Timer, and also I will cover design principles and design patterns raised. And next, the unit test and integration test held on Timer will be discussed. So first, let's start with program flow and algorithms. So as a timer used in game like LLK, it should address the following issues. First, it should terminate the game upon a failure and success of gameplay. And secondly, it should notify the caller when the timer stops. And to extend the gaming experience of the player, the timer should give bonus time or punishment time if the player successfully cancels grade or fails to do so. And lastly, the timer should update the progress bar, which is required by the GUI. So after studying online and trial and error, we finally came up with a reasonable design of the timer, which contains the timer thread and timer. They are two separate classes. So the timer thread class inherits from the thread class and behaves similarly like thread does. So you can call the start method of the timer thread to start a new thread, or you can call the interrupt method of the timer thread to terminate the thread. And also, the timer thread does timing and object state update. This is required specifically in the release 3.0 for the JProgress bar. And the timer thread also provides accessors to query data needed to other parts of the program. So what timer does is to encapsulate the timer thread and other operations to handle the timer thread. And also it provides APIs for other classes to manipulate and use timer. So here is a sequence diagram and a code block showing the core of the timer thread. So the wrong method will be automatically triggered when you call the timer thread.start method. So what it does is to update the JProgress timer thread bar and also do the timing. So when it just receives the call, it will set the value of the JProgress bar to e-time, and it will enter a loop. If the thread is not interrupted, it will run forever. So after 1 second, two current time will be recorded by calling the system.currentTime minutes, and also the value of the JProgress bar will be updated by 1. And if the value of the JProgress bar is larger than the 0.7 times set time, the foreground color of the JProgress bar will be updated to red, and if else, then the background color of the JProgress bar will be updated to a new color defined in RGB. And if the current time is larger or equal to the finish time, which means that the timer task should be stopped, then a flag will be raised and will jump out of the loop. And if the flag is raised, it will call the stop method of a stoppable, which is SP, and I will cover the use of the stoppable later. This is the core of the timer thread. And next, the timer task operations. So you're gonna do the setup, you're gonna start, and you're gonna cancel. So for the setup, you pass a stoppable object, and some random ints to the timer, and it will create a new timer thread object and passing the object, stoppable, and RT into the timer thread. And when you call start of the timer, if the timer is not running and not paused, it will call the start method of the timer thread to start the background thread. And if else, timer start error exception will be raised. By calling cancel, if the status of the timer is paused, it will return true, and the timer thread object will be refreshed. And if the timer is running, the interrupt method of the timer thread will be called to interrupt the background thread running and just make it stop, and the true will be returned. Else, if it's not running and not paused, then the timer terminate error exception will be raised. So this is a very important design of our timer to do the notification. So what we do is when we call a timer stop, it will call the stop of the stoppable in the timer. The stoppable is a field in the timer, and it will, as it calls the stoppable, the game page will implement the stoppable, and it will be registered in the timer as a field earlier when you set up the timer. And when you call stoppable will call the end game method defined in the game page, which is showed just in the code block here. So in the timer, when you call stop, they will update the elapsed time, it will read some flags, and will call stop. It will call stop of stoppable, and here the stop is just a game page. So in the game page, when you call stop, it will calculate some scores and call the game end game and return true. And this is how we do the notification handling, and this is how we transfer messages from a low level to high level. And for the add and extract time, when the function is called, if the timer is running, it will get the elapsed time and create a new timer thread object based on the bonus time you set. And if it's paused, and also the elapsed time just in the timer will be updated, and no timer thread object will be created. And if it's not running and not paused, a timer change exception will be raised. So next, design patterns and design principles. So in the design of timer, we used singleton pattern. This is because only one instance of timer class is needed. You will not see the situation where two game pages are concurrently running and two timers are concurrently running, right? So by adopting the singleton pattern, we avoid the creation of duplicate objects of timer, and we provide a global access to timer object at the same time. And for the dependency inversion principle and the law of Demeter, we can show these kind of principles using just one class diagram, which is basically the class diagram for the timer package. So the DIP tells us that the high-level modules should not depend on low-level modules. They should both depend on the abstractions. So this is true for our design. So from a high level to low level, which is from game page to timer thread, they all depend on an abstraction called stoppable, which is the interface. They do not directly depend on each other. And the law of Demeter tells us that each unit should only have limited knowledge about other units. So this is true because, for example, for the game page, it only has knowledge of timer, of how to get the instance and how to do the setup to do the start, but it do not have knowledge of the field in the timer, and it do not have knowledge of the timer thread. So this is an application of the law of Demeter. And the last one is unit test and integration test. So this is the test hierarchy diagram of the whole project. And what is highlighted here is the test hierarchy of the timer thread and timer. So we use bottom-up method, and here the timer thread will be tested as a unit test, and timer thread together will be tested as an integration test. So in the unit test of timer thread, we achieved a 100 pass coverage here in 6 test cases. And there is one stop for stoppable created because we do not want timer thread to depend on other kind of classes. But you can see that in some of the test codes, the coverage is not 100%. This is because that we used thread.sleep to manipulate time to achieve the 100% pass coverage. But by doing so, we need to surround it by a try and catch block. But the exception will never be caught. So this part is never reached. So there is some limitation, and this is on my master 100%. My master. So we proceed to integration test of timer. This is also used the method of bottom up, and it contains timer thread. And we also achieved 100% pass coverage with 26 test cases. And like what we did in the timer thread, a stop for the stoppable is created. And in the test cases, there is also some test code that is pass coverage is not 0. This is because first we used thread.sleep, just like what we did in the timer thread test. And also the second thing is that we used assert throws to assert or to attest exceptions. But by doing so, the code that raises the exception will never be executed. So this part is never reached. So this is why the pass coverage of the test codes is not all 100%. You can note that there is no code refactory of the timer. This is because that when the timer is created and designed, it is quite self-contained. It is quite reasonable and realistic. So the design of timer just did not change over the progress of the project. So what we want to do with the timer next is first to extract the object to be updated to be a parameter in the input. We do not want to pass the object step by step into the timer thread. It will be like too tedious. We want to just pass the object as one input, and that's all. And secondly, we will specify the operations to be done to the project when creating timer object by the user. So we do not want to specifically define how timer thread operates with the object. in the code of TimerStrap. This is too problem oriented, and we do not want the program like this. We will refer to the inline function in C++ or in Python, and we will try to achieve that. And thirdly, we will open functions that is developed but not used in LLK. So as you can see here in the class diagram, there are some methods like pause, restart, and pause, restart, or the stop, which is never used in the LLK. So if we want to extend the functionality of our program, this kind of functions will be used. So that's all of the timer of the LLK. And next, I will welcome
In the following time, I will talk about the scoreboard. For design principle and pattern. At first, we make all the records as a field of the scoreboard class, which makes the code messy every time the records are generated by the scoreboard. However, a record has its own function and field. Thus, we modify the structure of scoreboard and make record an independent class. The scoreboard will read all the records through the method inside the record class. It meets the requirement of single responsibility principle. Class scoreboard is a singleton pattern. Since logically only one instance of scoreboard will be called, by using singleton pattern, we save the memory from creation of duplicated objects. For program flow and algorithms. This diagram shows the process that the system obtains the game records from the file after the player triggers the button event. First, the system will judge whether the file exists or not. If it does not exist, an exception will be thrown. If the file path is correct, the system will read the file content line by line. When the line is not empty, convert the read stream into a game record and save it in the list until all the contents of the file are read. After that, the system will automatically sort the records in the list from large to small according to the score of each record. This block diagram shows the process that the system obtains the game record data from the list in the scoreboard. The system uses an iterator to traverse the list, returning the username, score, and time of each record, and storing them in a two-dimensional array for display in the GUI table. Next one is code refactoring. Before code refactoring, in the initial design of the scoreboard, the hash map is used to store the game records read by the system from the file. However, because the key of the map cannot be repeated, once repeated, the corresponding value of the key will be overwritten, which obviously does not meet our design expectations. In addition, putting the string array into the hash map through a series of operations is easy to cause various problems, unable to sort the scores and even unable to get the data normally. After code refactoring, we establish the class of the game record and give the record specific three attributes: username, score, and time. In the scoreboard, we remove the map but use the list to store the game record and sort according to the score attribute of each record. In this way, the structure of the code is clear. No matter reading and writing files or getting values are more orderly, and there will be no errors. And the last one is unit test. For unit testing, we tested each function separately. For each function, we designed several test cases to make conditional coverage and decision coverage reach 100% and maximize branch coverage as soon as possible. The test coverage is shown in these two pictures. That's all about the scoreboard.
Hello everyone, I'm Dong Qihua, and now let me talk about the testing method and bug report of our group. In testing, we use the bottom-up approach, and there are two reasons for why we choose it. The first one is that, as seen in the hierarchy diagram, our program flow is unidirectional, mainly from top to bottom, so it's natural to think of bottom-up approach. And secondly, the bottom-up approach is simple and relatively easy to implement compared to other methods we have learned. Now let's move to system test. As you see here, our implementation of system test is actually quite simple because it's hard to operate on a GUI project in the testing unit. So we just run the main function to see whether it can function normally. And now let's move to the overall coverage analysis. You can see the coverage for the whole project is 93.6%, and you can see each package's coverage here in the picture. And we use a total amount of 75 test cases to achieve the results. I found three features in terms of our coverage results. The first one is high in functional packages, such as in timer, in link algorithm. We all achieved the results nearly reaching 100%. And the second feature is low in some graphic package, which is GUI related package, such as the GUI package, such as the game package. And the third feature is the overall coverage result is still kept in a high position, giving credit to all of the group members. Now let's move to the bug report of our group. We use Bugzilla to write the reports, mainly because of its three advantages. The first one is that it has a widely covered report template. The report templates almost covered every aspect of the bug information, such as the severity, such as the priority, and all of the reproducing environments you can think of. And secondly, it's easy to check progress by just looking at the bug status in the bug report. And thirdly, it's a very good communication system. When creating the bug report, you automatically send emails and CC emails to your group members, and you can just add comments conveniently below the bug to communicate with your bug reporters and others directly. And here is one of the bug report from our group. You can see me, Dong Qihua, came up with the bug and posted it up at first, and David, Zhang Dehen, he seemed to find the solution of the bug and told me to try it. But later on, Sun has a deeper study on it, and came up with the final solution. And after the testing, I changed the bug status to resolved. Although the progress has made some detours, but the Bugzilla still made all of us clear about the bug information at all times.